2, 1, welcome in. When you're studying vectors, one of the applications, which I hope you're going to be running into, is the application of work. If you have studied physics prior to studying vectors, so for example, if you're in grade 12, and that's the time that you most likely are going to be studying vectors, you may have done physics, so either in grade 11 or possibly maybe you've done it in grade 12 prior to taking like a calculus and vectors course. Now, if that's the case, then understanding this video or understanding work makes it so much easier. However, even if you haven't done any physics, I think it's worth your time to know this applications of physics with respect to how physics defines work, or at least on the foundational side, because work can certainly be defined in several other possible ways and in terms of applications. But on the foundations, okay, that's what I want to present in this video. And that application in terms of vectors relates it back to the dot product. Now, when you study the dot product, the definition of the dot product and how to calculate it is not very complicated. So I have done the dot product. I can put up a link up above there. You know, you can apply the dot product and find out without actually knowing anything about work. However, what is really nice is that work is defined in the following way, which brings the dot product into existence for us in physics. And what you have is, okay, as I have written in here, work is really the energy or the amount of energy that is being transferred to or from an object. So it's coming to an object or it's coming from an object by applying a force along a displacement. Now, I have highlighted here force and displacement. And if you recall, both of these, so in particular force or displacement, force is an actual vector. It comes in with a magnitude and a direction. And the same thing happens in displacement. Now, if you've never studied physics, then obviously your intuition in terms of force may be not as great, but I have done several videos along the path of studying vectors that have talked about force and then how to calculate, and then you can break it down in terms of its components and then start doing all kinds of wonderful things. So I am assuming that you are familiar with what force is, really just a push or a pull in a particular direction. And I am assuming that you are familiar with the word displacement. And if you have studied in terms of calculus, so displacement, which is kind of abbreviated with an S, and it's a spatial thing, which is actually coming in with a magnitude and a direction, then it makes understanding work that much simpler. Now, I'll put up a link up above there where I talked about displacement, velocities, accelerations from the viewpoint of kind of calculus, and I did talk about it, in terms of trying to get some intuition into it. In this video, I just want to be able to tie in work with the dot product. Now, both force and displacement are vectors. So if we're going to be defining work, and if work is related to these, and in particular, as you can see here, it is applying a force along a displacement. Well, so if we wanted to have an equation for this, I can't just multiply force times the actual displacement. Unless, of course, they're in exactly the same direction. Then in that case, I can just multiply the magnitudes. But what if they're not in exactly the same directions? How would I actually figure out what work is? What does physics do in this case? Well, what physics says is that it is interested in the energy transfer, of the actual force and displacement that is combined together as they're working. And how it relates this back is through the dot product. So it takes the dot product between the force and the actual displacement. And now, if you've studied the dot product, then of course, we know what this is. You can actually do the dot product depending on how the force and the displacement is provided. Is it in a geometric in terms of representation, or is it maybe as a Cartesian vectors? And in either case, it doesn't really matter. We can find out what this work actually becomes. Now, because of the fact that you're taking the dot product, that means the dot product is actually a scalar. So what that tells us about work is that work is simply a scalar. Now, it also gives us what the actual units are. And for anybody who's ever studied energy, I'm sure you've run into joules, but you maybe have never known where it comes from. Well, notice that work and energy are related, right? Work is just the energy transfer. So they're kind of almost equivalent. So if it is a transfer, they have to have the same unit. And indeed, they do. Now, we know that force, for example, in the metric standard is given in newtons. And it is the metric standard for displacement, so distances. In that case, the metric standard is the meter. So, well, if you're going to multiply these two, so that is Newton meters. And it turns out that Newton meter, that is exactly what joules are. So joule is nothing else but simply Newton meters. So Newton multiplied by meter. Those are the units themselves. So now you kind of have an idea of what that joule is. It is force multiplied by the actual displacement, but it's not just a simple multiplication. It is actually the dot product because those two are vectors. And if they are given in, for example, geometric representation where we have a magnitude and a direction, then we know that the dot product can be given as simply the magnitude of our force multiplied by the magnitude of our displacement multiplied by the cos theta, where the theta just simply is the angle between the actual force and the displacement. So if I would draw this out, right? So if I have something like this, okay, and then I have something like this, and for example, this is my displacement, and this is the actual force that is being applied, and this would be the angle between them. And if you do that, the dot product, we certainly can, we will find out that we'll just get a scalar value, and that scalar value is going to have units of joules, which is just Newton meters. Now, a very special case, we know that if the angle between the two is 0, so they're in exactly the same direction, then what we do find is that when that angle collapses and it's 0, then cos theta is 1. So in that situation, the actual work is just the multiplication of the force times the actual distance, where the distance is the magnitude of our displacement that we are covering. And that is the most common thing that you run into physics. In physics, you typically start off with the dot product, but as you go along, you are simply just finding out what is the components, okay, in the same direction of the actual force, okay, or in the direction of that movement. Let's imagine that we have a box. So this box is just sitting on the floor, for example, and it's going to get pulled. Here is, the person who's pulling that particular box, and this box is, let's say, attached, okay, so to this person, like so, and this person is moving in this direction. And we can now find out, all right, well, if they're moving in a certain direction, so that box is going to be moving in that direction. It is being pulled, okay, by this person with some particular force. And let's give this some numbers. So let's say that maybe this force is equal to 100 newtons. And the actual force, so this is, for us, it's an actual vector because you're pulling and you can see that direction. Now, maybe, so again, I'm just kind of making this up, but we are moving in this direction, let's say, which is east, and maybe we've moved for 100 meters, for example, in this case. But as we're pulling this along, notice that we're creating an angle. So here is the angle in between the actual displacement. So in this case, it's 100 meters east. So those two are the vectors. And now if we wanted to find out the work which is done, all we do is we take the dot product in between them. Now, to take the dot product, we would have to know what that angle is. And that particular angle, so let's just, for simplicity, let's maybe call this, I don't know, let's call this 30 degrees, for example. So what you would do is you would just simply say, my work that has been done, which is the energy transferred, in this case, to the box as you're moving along all the way through that distance, it would have been the actual force direction, the force vector, multiplied by the displacement vector. And in this case, when I say multiplied, I'm referring to the dot product. So it's the dot product between the two. And what we would have is the magnitude of one multiplied by the magnitude of the other, and then the cos theta of the actual angle in between them. Now, this in general is not very difficult once you have those numbers. So notice it's 100 multiplied by, I guess it's 100 meters as well. And then the angle is cos of 30, right? So within here, I guess cos of 30 would be square root of 3 over 2. So that's from our unit circle. So within there, so that's square root of 3 over 2. And of course, you can just use your calculator if you wanted to in here. So you can certainly put this back into your calculator and multiplied by, this is cos of 30. There we go. So this would have been 8,660. I'll just round it. And this is Newton meters. Now, Newton meters is nothing else but joules. So you've calculated how much work has been done within here from the definition that physics provides us. And it is a dot product within those cases. Now, very often what we do is, if I drew this out, so if I have a force like this, and I know this is, let's say, 100 newtons, I know that this is 30 degrees, right? And this is my movement right there. Well, notice that if you broke this down, what you really are doing is you're trying to find what the actual component of that force is in the movement, or you can do it vice versa, okay, within there, because you can certainly take the actual component of the position, right, so that displacement, okay, it doesn't really matter which one you would take, but here you certainly know that the component that is in that direction, so this component right there, which is in the movement direction. So if that is my force right here, my general force, this is really the actual force in, let's say if this is the horizontal, this would be in the X direction here, but really it's of that direction of the movement. And of course, this equals to 100 newtons and cos of 30, right? Because we're just projecting. So we're doing a projection of the force, okay, onto the other vector. So we're trying to find what that component is. And you will remember that projections was another applications of the dot product. And I can put up a link up above there to that video if you want to study projections of one vector on top of another. And that's what work is. You're trying to find the projection from one vector onto another, and then you're just multiplying the two. And of course, if you would do this, the actual result, so this would have been the fx in the direction of that movement, which is just 100, and it would come up with exactly this. Of course, it's the magnitude of one multiplied by the magnitude of the other and multiplied by the cos of the angle in between them. Now, one other thing that I would want to be able to mention is that the definition for work from physics does bring about something very interesting, because the dot product that we have can possibly be 0, right? If the angle in between is 90 degrees. And so for instance, if you have your force, which is maybe in this direction, and your movement, which is in this direction, so your displacement. So you will notice that they are at 90 degrees. And if you take the dot product between two vectors that are at 90 degrees, the cos of 90 is 0. So there will be no actual work done. And when does this happen? It actually happens quite a bit in physics. Now, this is not a video intended to go over all the examples, but you can imagine if, for instance, you are walking around, a common example here is, and you're carrying a box. So with that box, to hold it up, you're going to have to exert a force to overcome gravity, which is trying to pull it down. And you're moving in this direction right there, right? So the movement is really negligible. You're just kind of holding it, but you're moving along and you're moving all the way through. You'll notice that, oh, wait a minute. Well, I'm exerting a force which is up to hold the box up, and then I'm moving along. And the actual work done on that box is going to be 0 because these two vectors are at 90 degrees to each other. Your actual displacement is in this case, and the actual force that you are exerting is actually up just to hold the box up. Now, please don't think, okay, that as you're going through, you're not exerting any energy. You're going to be exerting energy, but those, okay, are going to be differently, okay? That's due to the contraction in your muscles, right? So you need actually ATP, if you've ever studied about that, okay, in terms of the energy flow to hold that box up. Right? The muscles are contracting, so there is actual movement within there. You have displacements, you have forces, but that is what's happening within your body. This has nothing to do with the actual box itself. The box is being carried, okay, all the way through a distance. So that's what I wanted to be able to point out in this video. As you're studying vectors, and I'm sure you're going to see more examples of this, that the actual dot product has a great application in physics, and it is to do with the definition of work. And that's what you will run into if you're going to be studying physics, or hopefully if you're going to be studying vectors in general. So don't forget that you can take the actual force vector, multiply it with the actual displacement vector, and when I mean multiply, I mean the dot product in between them, and you can find out how much work has been done. All right, thank you for watching. That is it for this video. See you in future ones. Bye, everybody.